recap, we are looking at a.
Can you focus it? It's hard to see.
It's focus. I have auto focus and. How's that? So that's without the light on. Okay, so we're looking at a general exponential signal, A e to the bt, and we consider different cases with v0, a real constant, and so on. And finally, we ended up with a real constant. B, a complex number. Now the last case is what happens when A is a complex quantity. Right. As an example, we can go with let's say B plus J4. And B is also complex. Maybe something like -2 plus J5. Both are complex. And so our x of t becomes A, which is 3 plus J4, times e to the bt, which is -2 plus positive J5t. Now, this is something that we will encounter when we talk about Fourier series. And at that point, to be able to sketch this, we need to put it in a form such that, as we had back here, we can obtain the real part and the imaginary part, and then we can sketch each one individually. Okay? So towards the end, first we convert this from rectangular to exponential form. Now recall, this 3 plus J4 is 5 at an angle approximately 53.1 degrees, okay? Which of course in polar form we write it as 53. Okay? So that's what you want to use, and we'll see why. 5 e to the j 53.1 degrees, and then you have e to the -2t, and finally e to the j 5t. So the time variation is of course only in here, which is understandable because we have e to the bt here, and that's what carries the independent variable t. Right? Okay, so are we ready to sketch this? Well, not quite, because we still have these two terms. So what you want to do is to combine these two real quantities and then take care of the remaining two terms. That is, we write it as 5e to the -2t. So it took care of this, it took care of this. And finally that we have e to the j 5t plus 53.1 degrees. 5t coming from here, j53, that's coming from here. Okay? Now this case is somewhat similar to this case, with the difference that instead of the first term being a constant, it's also a function of time. Well, that's okay. We can still split this. Change this. How about this? Yeah, it's not aligned. So I'm going to watch. And also watch this to make sure it doesn't come back saying that it's waiting for some software to install. So watch that. Okay. So what you want to do is, you cannot do anything more than this. So we go ahead and tackle this one, which, being a complex function, we can use the Euler's expansion. Euler's, I'll put this Euler's, so where it says e to the j theta is cosine theta plus j sine theta. That's the expansion. So we want to use that. Yeah, it's saying e to the minus 2t. And open up a parenthesis in here. And e to the j, so that's cosine 5t plus 53.1. This is the first step, the real part. And then plus j times sine 5t plus 53.1. Close the parenthesis. At this point, now we take this term inside. So you have 5e to the minus 2t cosine 5t plus 53.1. And then the second term, again, we have 5e to the minus 2t sine of j. J is there. J sine sine 5t plus 53.1. Okay, that's plus here, plus j here. So now we identify this is the real part, and with this positive sign, excluding j, that's the imaginary part. Right? So what started out this in this form is now split into its corresponding real part and the imaginary part. Okay. And now we can go ahead and sketch each one individually. So that's how we can get the x of t graph. So now if I want to sketch the real part, well, that's a cosine function. But wait, there is this exponentially decaying function. And so we need to multiply these two. Product of these two is the real part. So let's go and sketch each one individually. So let's take this. How does this behave? 5e to the minus 2. What do you get at t equal to 0? 5. All right, because of this. And then it exponentially decays. So this. And of course, for t negative, it's continuous. You know, it goes up to infinity. Right. And how about this one? That's cosine function. At t equal to 0, what do you get for this function? Cosine of 53.1. Okay, so instead of starting at 1, cosine of 53, that's less than 1, so maybe something like this. So that's now equal positive and negative at least. And there is no time limit, so it goes on forever. So this is cosine 5t plus 53.1, and this is 5e to the minus t, and we need the product of these two. We need to multiply these two at every point. So for instance, at t equal to 0, you have some value which depends on cosine 53.1 multiplied by this, which is 5. So this is less than 1, where this is 1 here, negative 1 here. So product is less than 5. And then as this increases, this is decreasing. So yeah, it's going to increase because it's 5. times whatever you have, but eventually, because this is dropping down, you will not get, for instance, corresponding to the same value, you won't get the same product because this value is smaller. In other words, I'm going to make this as the envelope, which is going to go in light color, this. And this cosine is going to be between these two. Eventually dies down. And of course, here, for negative t, it is. Right? So this is the real part of x of t. Right? This value, is it 5? No. Is it 1? Yeah.
Your computer screen.
Thank you. It works, right? Okay. So is this equal to 5 or is it equal to 1?
It's 5 times whatever it equals.
It's neither 5 nor 1. It is 5 times cosine of 53.1. All right. How about this one? Can this be 5? No, because this function, which is multiplying to this one, in fact, this is the dominant one. Here, this is exponentially decreasing, whereas this is, going between +1 and -1. So this dictates eventually what this value is going to be. And so this is neither 5 nor 1. So the envelope is defined by this. So, I already have it here. So that's the real part. Right? Now what the imagined part? Exactly the same. The difference is it's a sine function. So time t equal to 0, it will be sine of 53.1. But other than that, the shape is pretty much the same. It's a decaying sinusoid for the real as well as the imagined. Right? Now that's important to understand because whenever we encounter a complex function such as this, we need to be able to sketch, to analyze what kind of a behavior the signal is having. So that's the last case for the exponential function. And now we move on to two other continuous time functions as well as their discrete time counterparts. All right. So the first is the continuous time unit step. These are idealized signal models. Right? Idealized because these are the ones that are going to be quite useful in analyzing signals and systems, although no signal comes exactly close to what we define here. In other words, you cannot go to the lab and generate a unit step signal. It will be very close, but not strictly equal to it. So if you cannot generate this, why would you want to use it? Because it simplifies the task. And we say, the proof of the pudding is the eating, right? So, yeah, it's not exactly the same, but the results agree with experimental values. So that's the justification. Right? So with that, let's define this unit step in 2 steps. Right? It is 0 when the argument t is below 0. And it is 1 because it's unit when the argument t is greater than 0. What happens when it is exactly equal to 0? Well, you might say at 0 minus, it still continues to be 0, and at 0 plus, it makes a jump to plus. In other words, you sketch it like so. The area. So it is 0 for t less than 0, and 1 for t greater than 0. And at exactly 0, you can say it jumps from 0 to 1 in 0 time. And that's what makes it ideal. No physical signal can jump from one level to another in 0 time instant. It may have 1 microsecond, 1 picosecond, 1 femtosecond, as small as you can think of, but it can never be exactly equal to 0. The transition from one level to the other cannot be in 0, and that's what makes it an idealized model. And we say, well, that's okay. I can live with this not being practical, because practical signals can be treated as close to making this transition. Okay. So if you want, you can say u of t at 0 minus, because we're coming from here, first we encounter 0 minus is 0, and u of t at 0 plus is 1. So in 0 time instant, 0 minus to 0 plus, the difference is to 0, it makes a jump from 0 to 1. Okay. And this is a very important signal, because any system that we're going to analyze, we want to look for its response to such an input signal. Yes.
So what's its value at 0?
There is no such thing as 0. Some people define it as half, but it makes more sense to go from 0 minus to 0 plus with a value of 1. And the reason for that is, in fact, the only time we would ever require values at 0 minus and 0 plus is when we talk about the initial condition, the initial value, when we talk about Laplace transform. At that time, we can use that. All right? The key here is it's not a continuous function. It makes a jump discontinuity. And that's what you got to remember here. And same thing with the next function also. Okay, so some properties we want to get at. It's unit step, because the amplitude when it is not 0 is 1. Okay. You can have a different value, say x of t is 5 times u of t. U of t is already here, and you're multiplying it by 5, so it's going to look like this. It's the same function, except that it's scaled by 5. So it's 0, and then it jumps to 5, and that's our example. Oh, it continues. There's no time limit, it's going forever. Okay. You can also have, say, some g of t, negative 3 e of t, which will be then 0, and then it jumps to negative 3, and then continues forever. So that's our g of t, and so on. All right, now based on our delay properties, that we have seen earlier, what if we define a signal y of t as 2 u of t minus 3? So where will it start, and what will be its value? So we want to sketch y of t. Where does it start? First, let's, again, whenever you encounter something like this, you split into simpler things that we can easily sketch, things we have already seen. That's a constant. You scale it up by 2. That's what it says. Instead of unit, you multiply it by 2. Okay, so the amplitude is going to be 2 times. How about this? It's unit step. All right, knowing this, it's delayed by 3. All right, so which way will it start? To the left or right of the vertical axis?
Right.
Okay, so this is 0, and here is 3, and up till then, it's 0. Okay, and then it makes a jump to what value? 2. And continues. All right. And again, I want to emphasize this point. Anytime you have a unit step, as well as the next function, just look for the argument. All right? When the argument is positive, that's where the function exists. All right? And then you can put the scale. Okay. All right. I'll give you 5 seconds to sketch this next function. Let's say we have x, y, g. Let's go with the f of t. Say f of t is let's go with 2 u of t plus 3. I'm opening the left parenthesis here. U of minus u of t right, go ahead and make a sketch, and then I'll talk about that. And whenever you're in doubt, just like we did here, 1 second, just like we did here, take the first function, sketch it. Take the second function, sketch it, and then take the product, point by point product. So you may want to sketch this one, you want to sketch this one, and then instead of multiplying, you're subtracting the second function from the first function. Okay? Incidentally, your quiz on Thursday will be related to these signals, not on complex numbers, which we will postpone, or just when we are about to talk complex numbers. So right now, we'll stick to this. Okay, so did everyone finish? Let's go with the expansion of this. T plus 3 minus u of t minus 3. So I took this t inside, and now let's sketch each one. This is the origin. Where does this function begin? Negative 3. That is, you look for the argument. When does the argument become 0 or positive? Only when t is minus 3 or above. Right? I'll keep repeating this another 15 times or so, because that is the key to sketching and hence analyzing the signal. Look for the argument. When does the argument become 0 or positive? That's when the function exists. Okay? So it goes to negative 3. All right, and they'll go positive, negative. What's the value? Is it 0 up to negative 3?
Yes.
Yes. Because if you pick a number like t equals negative 5, negative 5 plus 3, that will make it negative 2, and unit step for a negative argument is 0. All right, unit step for a negative argument is 0, therefore this is 0. Whereas if you have, say, negative 3 or negative 2, negative 2 plus 3, that gives you positive 1, the unit step exists. So then it goes like this, with a value 2. All right, it's 2, and it goes forever. So this is this one. Here is 0. Right? Now let's look at the second one, and we'll do the subtraction after that. So we'll just sketch this. All right, where does this begin?
It begins with 3.
That's plus 3. So up until then, the argument is negative, therefore unit step function doesn't exist. And then once t is 3 or more, the argument becomes positive, so you have the function having a value of plus 2. So that's this one. Now we need to subtract the second function from the first. So what do you get?
Basically, up until negative 3 is 0.
Up until negative 3, both functions contribute 0. 0 minus 0 is still 0. So yeah. All right. And at negative 3, this is giving 2. The other one is still 0. So 2 minus 0. Notice this negative sign here. So that's where it starts.
It's like that until 3.
And goes to up to 3, because there is no contribution coming from this function. So you're subtracting 0 from 2. So all right. And now 2 and 2. 2 and 2 everywhere cancel out. So it goes back. All right. So this is f of t. So that's how later on in Fourier transform we will define a pulse. It's a single pulse. It doesn't repeat. It just occurs once. All right, and the duration of this pulse is from -2 to 2. All right. So you can also define, for instance, f of t So this is one way of defining FOT. The other way would be that it has a value of 2 as long as -3 less than or equal to t less than or equal to 3 and 0 elsewhere. It is 0 everywhere else. It's only existing from -3 to +3 with a value of 2. Let's see what other dimension. Yeah, that's right. So the step functions are useful in analyzing a system for step response, and that is something something like this. When you want to see, well, I want to merge with the highway traffic. All right, how fast can I go from 0 to 60 miles per hour? How long does it take? 5 seconds, 7 seconds, 7.3 seconds. So 0 to 60, I want to jump from 0 to 60. Typically, it won't be making the jump in the 0 time. It'll probably do same thing with an RLC circuit. So you have a step input, and you want the response to follow this in shape. But typically, if you have a single time constant element, it'll be going exponentially to reaching it. So if you have two energy storing elements, such as an inductor and a capacitor, it may oscillate for a while and then settle down, or it may be oscillating for a longer period. And if you're not careful, it may oscillate forever also. So that's where the importance of finding the step response of a system comes in. We talk about a single time constant case or the case with two energy storing elements. You can extend it to many other similar systems. Okay. All right, now, equally important, if not more so, is the next one, which what did I call the first one? That one. Continuous time unit impulse. Instead of giving this definition mathematically, let's look at it from a physical point of view. Okay? So I'm going to consider a signal, and I'll call this some GFT versus T, and this is a pulse similar to this, except I'm going to use variables. So it's going to be, I should have drawn minus A to A, and a height of 1/2. Say, for instance, as we have here, minus 3 to 3, and the height of the pulse is 6, something like that. But keep in terms of variables, all right? Now, let's find out the area. So it is G of T dt going from minus infinity to positive. What is that area?
1.
The 1?
1.
Because it's a rectangle, all right? Width of 2a and height of 1/2a, so it's just 1. And once again, do not try to come up with an expression and then try to integrate this. All right? Don't write down an expression, something like this or like this, and then you will get stuck. Hey, how do we integrate a unit step? We never talked about this in class. Do not do that. It's a simple rectangular function. It's a definite integral. We know from minus infinity to minus a, area is 0. From plus a to plus infinity, area is 0. So the only interval we need to be concerned about is this interval, and in this interval we have a rectangle whose area is. Right? So keep that in mind. Now, what I'm going to do is I want to take the same rectangle, except that I'm going to shrink the duration by a factor of 2, and correspondingly, I want to lengthen the height. In other words, I'm going to have, instead of minus a to plus a, I'm going to have minus a over 2 to plus a over 2. What's the width now? A. Instead of 2a, it's now a, and so the height is 2. Again, if you want, you can call this G1 and G2. These are different functions, so you can still use the same name. So G of t minus infinity to infinity. Still 1. All right? As long as you're talking about the area, which is what the definite integral implies, it's still 1. Go to the next one. Every time I go from one step to the next, I'm having the width and then doubling the height. So this time I'm going to have a over 4, negative a over 4 to positive a over 4, and the height is correspondingly raised to 2 over 4. Doesn't look good. And this is what now I'm defining as GFT. So this is 1. Still 1. Right? We are not interested in defining this function without its integration. We do not say, oh, this is what g of t is. We never said, oh, g of t is 0 from negative a to minus a and plus a. No, we're not interested in that. We're only interested in the area. That's why g of t is never appearing, something like this or this, because we're only looking for the area. Right? That's the key concept. You are only looking for the area. So if that's the case, what happens in the limit? That is, I cannot show that, and nobody can show that, but in the limit, when I have extremely small width, and correspondingly, I have 1 over that extremely small width. All right? So, I can't even show this graph. So let's call this sum W, which is the width. Then this is 1 over. Again, minus infinity, g of t to t is still 1. You have a finite value here, you have a finite value here, 1 over that. So the area is still. Keep doing that further. Maybe it's 10 to the minus 9, 1 nanometer or nanosecond in width, and 1 over 1 nano, not in time units, but whatever the height is. Still the area is 1. Right? In the final case, we say, well, what if the width is 0 and the height is proportionally 1 over 0, which is infinity? What would be the area? It's still 1. All right? That's somewhat hard for us to fathom, but by the process by which we are creating this function, that would make sense. As long as your height is 1 over the reciprocal of the width, the area is always 1. So we say in the limit when width goes to 0 and height goes to infinity. Nothing has changed. This area is still 1. And this is what we are interested in. We are not interested in, hey, how much is the duration of the pulse? How much is the height of the pulse? No, we are not looking for that. We are only looking for the area. And as such, now we don't want to call it g of t in the extreme case. We want to call this simply some delta of t. Right? This is the delta of t. And we are looking for the area. So this is the function name. So we're looking for the area going from negative infinity to positive infinity. Delta of t is 1. Because it's the limit, this is part of the definition. The other one part of the definition, the other part is that delta of t is 0 for t not equal to 0. It's 0 everywhere except at t equal to 0. But we're not looking for the value per se at t equal to 0, rather we're interested in the area of the whole function. So these two go together. You cannot just go with this alone. Now can you just say this definition? They go together. It's 0 everywhere. Okay? It's 0 here. It's 0 here. Except at t equal to 0. And can we say the amplitude is infinity? Well, not really, because we're only looking for the area. So we have a special notation for that, where we use the arrowhead to signify it represents the area being equal to 1. And that's our delta of t. Delta of t is defined as 0 everywhere except at the origin, or to put it in the form similar to the unit step, it's 0 everywhere except where the argument becomes 0. This is where the argument becomes 0. And corresponding to t equal to 0, that is when the argument is 0, we do not give the amplitude, we just give the area. All right? Once again, look for the amplitude. Where is it 0? That's where, if you integrate, you get an area. All right? If you follow this, all right, and of course you have to use this arrow. Let me ask you this. What if nothing has changed? It's still the same delta of t. I give you this delta of t, and this is the definition. Now tell me, what's this value? Say minus 3 to plus 4 delta of t dt. What is this?
1.
It's still 1. Because the location where the impulse is present is included in your area calculation. All right? There is no area coming here. There is no area coming here. In fact, if you look at this, delta of t is here with 1. So when you go from negative 3 to positive 4, there is no area up to this point. In fact, there is no area from negative 3 to 0 either. Nor is there an area from 0 onward. It doesn't matter whether you go up to 4 or 5 or simply 1. It doesn't matter. So long as this instant is within this interval, you get an area. Right? Go further one more step. That is, what if we have some infinitesimally small value, some epsilon, and it's positive. What is that? You can define epsilon limited by our imagination, maybe 10 to the minus 15. All right. What would be the area?
1.
It's still 1, because the interval includes 0. And that's where the impulse is present, therefore this 1 comes in. That's the area, so that 1 comes in. Okay. So once again, remember this. Whenever we talk about delta of t, and we're going to do that for the delayed case as well. So whenever we talk about this, always look for the value of the variable, here it's t, that makes the argument go to 0. Here t equal to 0 is where it's 0, therefore as long as that instant is included, you get an area. All right? That's unit. That's unit impulse. If we have, say, some g of t equals 5 delta of t. How will that look like? Well, here is t, 0. You can have this height proportional to the amplitude here, so it's. So this is our 5, because that signifies the area. as a matter of fact, if we go ahead and do this, says from minus epsilon to plus epsilon, or minus infinity to plus infinity, as long as 0 is included, g of t dt, which is minus epsilon to plus epsilon, find delta of t dt, and that is this one. You will pull this 5 outside, so you end up with, instead of 1, now here it's scaled. Right? Okay, let's go ahead and delay this unit step. So maybe I have a function g, of f of t is delta of t minus 2. Okay. So how do you sketch that? Look for the variable, the value of the variable where the argument becomes 0. So this is going to be present when t equals 2, and because there's nothing here, by default it's 1. Okay. So this is our f of t. I said f here, so it's f of t is this impulse which is delayed by 2 seconds. And if we have an amplitude of, let's say, 4, then I would have 4. Right? Now, let's find the area of this f of t. Right? Going from negative infinity to 1. 0. All right? By sketching this, you realize, okay, I'm coming from negative infinity, so all the way from here, and it's all 0, so nothing coming in here. There is 1, so this is 0. Which you can see from here, 4 delta of t minus 2 dt, and that's when you realize, hey, this is present at t equals 2, and I'm not covering that instant in my interval, all right, which is outside the integration interval. I've run out of space, I'll simply say outside interval. Outside the integration interval, therefore the answer is 0. You are not including the impulse area in your integration, therefore the result is 0. Right. Now let's get some properties. The first one, I think, so instead of jumping to properties, I'm going to illustrate this first. Let's go with, I'll sketch the first. Some impulse function, say something here. We may have a height of 3, and it's occurring at, so delta of, how do you write this one? Delta of t minus 2. T would have been here, minus 2, so you're delaying by 2 seconds. It's just minus 2.
And if it goes to 3, then you're
yeah, and the height is 3, therefore you put it here, or you put it outside, that's a constant. Okay. So if I go from, let's say, 2 minus epsilon's output, the 2 minus 10 to the minus 15 to 2 plus 10 to the minus 15. What would that be? It's 3. Right? Because I'm only including this tiny interval in my area, and of course that includes the location of the impulse, therefore it's 1, and times is 3, so the height is 1. Okay. But if I do the same thing, from minus infinity to 2 minus 10 to the minus 15, or 2 plus 10 to the minus 15. So yeah, 10 to the minus 15, you can replace it with some epsilon or any small value. Okay, I'm just picking that up. So what's this and what's this? 0. Both cases 0. You're coming from negative infinity. There's nothing here, nothing here, nothing here. And then you're stopping just an instant before the occurrence of input. 2 minus. This is occurring exactly at 2, but you're not including them. Therefore, it's 0. Same thing. You skip this, and then you're finding the area again. It's 0. Okay? So now generalize this. Let's say, let's go with this quantity. The delta of t minus some t0. Remember, this is always a constant. Anytime you have a subscript, that's a constant, fixed value. Right? And so you have, let's call this positive. So T0 minus epsilon to T0 plus epsilon. How would that be? We are including the location. This is located at T0. All right, T0 is positive. I'm saying positive here, so something like this. And I'm going 1 instant before to 1 instant after. So I'm including this, so that's it. If I had k times that, I would have k times that. The idea is, when you find the area, the interval should include the location where the impulse is present. Okay. So here it's not, it's aligned on the screen, but it's not aligned with this. So that, okay. The next one, this key property is this. Okay. So this is where we're going to talk about the sifting property, something that filters out. And this is the one that we'll be using over and over again. So let's get a good handle on this one. All right, we have a function x of t that's continuous. Not a discrete one. It's continuous everywhere. Say something. It's something that I can easily reproduce, but not as so. Maybe t versus x of t. And I'm also defining, say, another function g of t, which is, this is some arbitrary, so I'm giving it in graphical form, and g of t is delta of t minus 3. So g of t looks like that. Incidentally, you can also have negative area, in which case the arrowhead will point downwards. Okay, just trivial, but I want you to remember that. Okay. So here is g of t. 0. All right, now I want to find the area of the product. It's x of t times g of t times g of t. Well, that's undefined because 0 times any value you have here, 0 here, 0 here, but except at this point, and this is having an amplitude of infinity times this, it's meaningless. So instead of just finding the product per se, we want to find the area of the product. Okay? If it weren't for the integration, the simple product would not have made any sense because one of them is infinite. Right? And that's never going to be of any use for us anyway. So we are multiplying these two functions, and then we are finding the area of the product. So intuitively, what would we expect the product to be? Say coming from minus infinity to 2. What would be the product? 0. So what's the area? 0. Right? Likewise, going from say this point onward to plus infinity and multiplying with this, again, something times 0, something times 0, something times 0. Product is 0, area is 0. But when it comes to exact location where the impulse is present, so this is where I'm going to write this as arbitrary function x of t times delta of t minus 3 dt. I'm replacing g of t with this. Right? As a matter of fact, I'm going to split this, and you don't have to change it, just follow along. Maybe I'm going to finally come back to this. But if you feel like you want to change it, that's okay. Say I go from negative infinity to 2. So what the upper limit is 2. So what would the area be? 0. Because I'm coming from negative infinity to 2, and in that interval, 2, in that interval, one of the functions is contributing 0. So when you multiply 0 with the other function, and as long as that's not infinity, because 0 times infinity is indeterminate anyway. So as long as the other one is not 0, or not infinity, the product is 0, therefore the area is 0. Right? Putting on to these two. Likewise, you also go from, let's say, 3.00001 to infinity x of t delta of t minus 3. What would it be? Again 0, because this term is here where it is, sure, it's on screen, where it is 0 times this, product is 0, again, area is 0. All right, so it makes sense. Well, yeah, we ruled out, there's two cases, so when there is this instant which is included in the integration range. So now we go back to our original question, x of t times g of t dt, which is minus infinity to infinity. Some arbitrary function x of t, delta of t minus 3 dt, and what do you have at that point?
X of 3.
That's the correct answer. So let's see how we get there. Right? So at this instant, whatever value this x is having, all right, that value multiplied by this delta of t, and then we're finding the area. So let's take this one here. So it's minus infinity to infinity, x at 3 delta of t minus 3. Why only 3? Because that's where this is present. And if this is not present, then it doesn't matter what value you have, the product is going to be 0, so the ultimate result is. At 3, this value multiplied by this, so you might be tempted to say, oh, at 3, it's x of 3 times delta of 0, and this is infinity, so therefore the product is, no, we're not interested in that. We're only interested in the area of this product, not the individual values themselves. So, does everyone see this? Well, that it's only x of 3 that has non-zero value, the product, right? Is that a single value? Yes. Therefore, we are allowed to pull that outside. That's not a function of time anymore, so you pull that outside. And then what do we have? We are only integrating, by this function, we're only integrating this function from negative infinity to positive infinity. Sure enough, it does include the location where it's present. So what is the single value? That's 1 times x of 3. So it's x of 3. Right? So in this process, when you have these two functions, one of them being the impulse function, we are able to get the value of the first function, x of t, at the location where the impulse is present. The impulse is present at t equals 3, and that's what's pulled out by this integration. Now, this is not having the units of area. This is simply the value of the function. So the value of the function is now filtered out by this process of multiplying with an impulse function and then finding the area of the impulse function. All right? So that's what we want to generalize. So we want to say that the shifting property goes like this. Minus infinity to infinity, some function x of t, delta of t minus t0 is x of t0. And that t0 comes from the argument for the delta function, which will make the instant where it is present, where it is existing. Right? And that's why I keep saying you need to look for the value of the variable. T is the variable. T0 is a constant. Value of the variable that will make the entire argument go to 0. Right? So only t equals t0 is a value that will make the argument go to 0, and correspondingly, what's the value of the second function? That's what comes out. All right? So let's see what else. The properties. Oh, yeah, this one is another key property, and then we can relate to the previous function, and that is, let's say we want to go from again. Let's illustrate first, and then look at the value. Let's see. We want the area going from negative infinity to positive 3 for this delayed impulse. So let me sketch that. And delta t minus 4, so this is where the impulse is present. So that's in here. Okay. So what's the area for the integral? 0. Because that's not included in here. All right. How about if I go from negative infinity to 5 delta t minus 4. Well, because starting from negative infinity, you are covering the instant where it is present, so it's 1. Okay. Now you want to generalize this. Okay. Again, I want you to be comfortable in using any variable. So instead of t all the time, maybe I'll use alpha. Okay. And 0, maybe this time I'll have it over 3. So how would you define this analytically? Well, alpha is the variable, and when alpha equals 3, that's where the impulse exists. So this will be delta of alpha minus 3. Once again, look at this. What would make the argument go to 0? Alpha equals 3. And that's where it's present. So the variable is the key. Okay? Now, we have two cases here. So if I go from minus infinity to some value, I'm just saying value, but I'll use term something like, let's not go t0. To avoid confusion, I'll use t0, and then I have delta of alpha minus d alpha. Remember, the variable is alpha. Okay? What would that be? Well, the first question you will ask is, what's the value of t0? It depends on that. Everyone see that? Suppose my t0 is 2. This t0 is 2. What would be the answer? 0. If t0 is 4, that's 1. So we open up the possibility for two cases. it is 0 if t0 is what? Again, I'm going to throw some examples, then you generalize. Suppose my t0 is here or here. What would be the integral? 0. All right. So t0, the integral is 0 if t0 is. All right. One more time. This is a key concept, so I want you to understand this clearly. Okay. Let's say t0 is 2. What will be the integral? Minus infinity to 2 delta of alpha minus 3. What would it be? 0. Okay. t0 is 3.00001. I'm covering where this is present. So it's 1. All right, as long as my integration interval includes this instant, my area is 1. In this case, it does not. In this case, it does. 3.00. Again, you can put as many zeros as you want here. All right, as long as it's included, it's 1. So now tell me, if t0 is less than, and it is 1 if t0 is greater. Here it is greater. But you cannot say equal because that's exact. All right? You cannot. Well, that's why I put this. But when you say equal, for all intended purposes, we can say, no, that's equal. You have to go from 3 plus 10 to the minus 15. Is that equal to 3? Sure. Okay. So just to be on the safer side, we don't want to say exactly equal. All right. So here is the. So if it is 3, this what goes in here. The 3 goes in here. Okay. Now, go one more step in generalizing this. Minus infinity to t0, delta of alpha minus, say, some big T. Another constant. These are constants. Not variables, but constant. Alpha is still the variable. Okay. So, what would that be? Just as we have here, okay, it will be 0 if t0 is less than t, whereas t is now 3 here, okay, and it is 1 if t0 is greater than. All right. Now, suppose I'm calling this area as maybe some GFT. Now, how would you sketch this GFT? Remember, GFT is the result of performing this integration, which is given here. So, how would the, and let's say our T is, say, 5. Just for illustration purposes, let's say T is 5. So, how would this GFT look like? If you want, you can put this 5 and 5. See, this is 5, and 5 is 5.
Okay, so
Up to 5, it is 0. GFT would be 0. All right. And then at 5, it makes a jump transition. That's 1. Everyone see that? Any difficulty? What if my t is -3? Then how would it look like? Remember, this on the left hand side I have t. All right, I have t and I should have said t0. Yeah. Okay, because it depends on this t0. So if t0 is below t, or t0 is above t, so that's negative. Okay, so t0. Okay. Even though t0 is a constant, right, for a given value, because these values depend on what value you are giving for t0. That's why I'm using it as a variable. Even though when it comes to integration, that's a constant. Okay. Now, if t is negative 3, how would the function look like? G of t.
Shift it.
It's going to start at negative 3, and then, okay, now, tell me, how else can you put this G of T0? I have defined G of T0 in this manner, which I evaluated to be like so, and that's what is shown in this diagram. Okay?
T plus 3.
Using the previous unit step, how would you put this in? Does it look like a step function? Yes, it does. And is it delayed? Yes, by 5 units. Okay, unit 5 seconds or 5 time units delayed. So shall we say it's u of t0 minus 5. This one. When t0 is 5 or above, you have a value. When t0 is below 5, you have 0. The argument is positive, you get a value. The argument is negative, you get a value. How about this one? This will be u of t0 plus. Right? Okay, I don't want to call it 3, but I want to use this t. So I want to rewrite it here. So again, keep in mind this alpha is the integration variable. It's the variable for the function delta, right? And of course, when you complete the definite integral, this alpha is not going to show up anyway. It's a definite integral, it's going to vanish. So you can call it alpha, you can call it beta, or you can put any symbol that you can think of. All right? Ultimately, the limits will be substituted, and so the integration variable will not appear. That being the case, I'm free to use some t. Right? So what will this be? Looking at the two cases, looking at plus 5 and minus 3. Okay, so how would you write that? Delta function will integrate to 1 provided the limits include the location where it is present. So until then, okay, suppose this t is less than t, which is the case when I go when I go up to this point, it will be 0, and it's 1 if t is greater than t. If my upper limit covers the location where the impulse is present, then I have an area. If it does not, if it stops short of where it is present, I have 0. Okay? How can you write this in terms of unit steps? T minus. That's the t that appears here. And it depends on this constant big T. So if this upper limit is below big T, it is 0, so this is 0. Okay. If it includes it, you will. In other words, the unit step is related to the unit impulse via this property. Well, for simplicity now, I'm going to make this upper limit to be 0. Now what do you have? You can do this independently or you can use this. So let's try to do this independently. I didn't know anything about this.
If t is greater than 0.
Exactly. I'm going to evaluate this afresh. I did not know this previous property. So I have this impulse function. All right. This is delta phi alpha. And I'm trying to integrate this function. This upper limit is a value, a single value. So maybe my t is in here, so area would have been 0. Or if my t is here, or here, or even here, area would have been 0. Right? That is would have been 0 if t is less than 0 because that's where it's present, and 1 if t is equal. Isn't that u of t? When the argument is positive, 0. Alright? When the argument is positive, or 0 positive, that's when I have 1. If it is negative, I have 0. So unit step is related to the impulse function via this function. Now, this gives the area of, so u of t is negative infinity to t, delta of some argument, d of that argument, and that's how you connect these. How about the derivative of this? What's the derivative in here? 0. What's the derivative in here? 0. It's a constant. The derivative exactly at 0. You are making a jump from 0 to 1 in 0 time. So it's infinite. All right? But again, you look at the area, it's 1, so it's always delta of. The two properties that we will use when we try to find system response, where maybe this is known, but we want to know the response to this, or the other way, then we can use these two properties. Yeah, we can close. So let me return the quiz. Yeah, we know that. I was going to do this example 2.5. Maybe we'll start with that third day. Let me see. Brad, do you have a session this week?
Yeah.
When?
Today at 3 to 3:50 in Anderson 224, and then tomorrow 11 to 11:50 in ECE.
So could you please go over this example 2.5?
Yeah.
All right. It's an example, worked-out example, so you know how to read it. If you cannot make the session, just go ahead and read that. We have covered, all the material that is related to this example. But if you do go to the session, it will work.